Alright, in this movie I'm going to review chapter 17. That's about reaction rates and equilibrium, characteristic of equilibrium, application of equilibria, and kinetics. So, equilibrium reactions. So we have, for an equilibrium reaction, we have the forward reaction is to the right and the reverse reaction to the left. And the reaction continues all the time, but at some point it's not changing. Well, what's not changing? The concentrations are not changing anymore of my reactants and products are not changing anymore. We still have the reactions, forward and reverse, but concentrations are not changing anymore. They're constant, and then we have an equilibrium. So you can see in this picture as well. Here, concentrations are changing, and from here on, the concentration of NO2 and N2O4 are not changing anymore, and that's the moment we have the equilibrium. So equilibrium means the rate forward and the reverse of my reaction are the same. Equilibrium expression, K. So, products over reactants. My reaction coefficients in my balanced equation become powers. And we're only going to include gases or particles that are in solution. You can see here my favorite one, N2 plus 3H2 become 2Na3. My K is concentration of Na3 to the power of 2 divided by the concentration of N2 times the concentration of H2 to the power of 3. You see coefficients in my reaction equation become powers in my K expression. And concentration is always moles per liter. And the value, when we have plug-in values for the concentration, we can have a value for K, and we call that an equilibrium constant. We talked about ICE table. Sometimes we have to use an ICE table. I stands for initial change, and equilibrium for the E, to find the concentrations of my compounds in equilibrium stage. And important for the C row is that C, the values over there in the C row of my ICE table, correspond to the mole ratio of my balanced reaction. So, and when we have a value of K, that's constant. It's only going to change when my temperature is changing. So we can change the volume or whatever, but K is not changing. Only changes when I have a different temperature. So then we talked about homogeneous and heterogeneous equilibrium. Homogeneous, when all my compounds have one physical state, so gas, liquid, or solid, or solution, and heterogeneous, more than one physical state. So the first one, it has S, S, and G, so that's a heterogeneous equilibrium. And here we have solution, solution, solid, also a heterogeneous equilibrium, because I have more than one physical state. Shifts in equilibrium. That's not the next topic. Le Chatelier's principle. So when it changes on a system, the system wants to shift back in a direction that tends to reduce the reduce the effect of that change. So we talked about a couple changes. If I have an equilibrium, if I'm adding reactants, shift to products. Adding products, shift to reactants. If I remove products, so then reverse reaction will happen less, I shift to products. Remove reactant, shift to reactants. Then decreasing or increasing volume. If I decrease a volume, that means it's the same as increased concentration. Then my equilibrium shifts to the side with the smallest number of particles. So you can remember that. Decrease, smallest number of particles. Increase. Volume, same as decreased concentration. Then it shifts to the side with the largest number of particles. So decrease, smallest, increase, large number of particles. And then about temperature. Temperature, cable change. It's not important now. Increase of temperature, equilibrium shift to the endothermic side. Decrease temperature, equilibrium shift to the exothermic side. You have to look carefully at the question to find out which if the forward or the reverse reaction is endothermic or exothermic. If my forward reaction is endothermic, my reverse is exothermic, and other way around. So we can also apply the equilibrium constant. If K is much more larger than 1, we know my equilibrium is on the right-hand side, products. If it's a lot smaller than 1, it's on the left-hand side. So a couple applications. First of all, if I have K, but I do not have all the concentrations of my compounds in equilibrium, we can find out the concentration of the remaining compound. So here we have information of PCl5 and PCl3. We know K. We can plug in all the numbers and finally we can assess the concentration of CO2. A different one was the solubility products, solubility equilibrium. So if I have an ionic compound, some will dissolve very good and some will dissolve really, really poor. For this one, Pb lead chromate, PbCrO4, a little bit of lead, 2+, and a little bit of chromate. We can see this equilibrium. We're not going to include the solids, so my KSP stands for solubility product, is concentration Pb2+ times the chromate. We can also do the other way around. When we know the solubility, so we can then assess what is now my KSP. Because when we know, let's say for barium sulfate 3.9 times 10 to the negative 5 moles dissolve, then I have the same amount for barium ions and the same amount of sulfate ions. When I multiply these two, then I have my KSP. So that's a different way of the application of my equilibrium constant. Kinetics, finally, reaction rate. We know there are 5 factors that influence the rate of reaction. First, type of reactant. Some reactants don't react and others are pretty good. So it's a characteristic of my reactants. Some compounds react, others not. Surface area. Larger surface area, more reactions. Or in terms of the collision model, more surface area, more possibilities for collisions. So for reactions. Concentration. Increased concentration, increased number of particles, more chances for collisions. So that means more reactions. Increase of temperature, molecules have more space, more speed, sorry. So that means more energy, more speed, more chance for collision, increase of reaction. Presence of a catalyst. A catalyst is not part of the reaction itself, but made the reaction possible. Increase of reaction rate. So to explain this, we can use the collision model. A collision can be seen, a chemical reaction can be seen as a collision. And for an effective collision, that's a chemical reaction, my particles, that can be molecules or atoms, need to have the right speed and the right direction. So the rate of the reaction, we can express it as a symbol S, and that's the change in concentration over time. Moles per liter per second. Moles times the liter to the power of -1, seconds -1. Rate law. Because concentration is one of the 5 factors, we can express it in a rate law. S, moles per liter per second, is K, that's the rate constant, times the concentration at the T is 0. So in K, the value or the unit from K can depend on my rate law. So for here, when S is K times concentration A, S only depends on concentration of A. So moles per liter per second for S, and this is moles per liter, so K must be 1/2. And it can be different for the final 2 situations on this sheet. So when I have A to B, a possible rate law can be S is K times A to the power 1. We call it first order, because that's the one over here, first order, and only depends on one reactant. To A to B, that's the second, as you see, A to the power of 2, A squared. And that's why second order. And the rate law, the rate only depends on the concentration of A. For here, it's a possible one could be A squared times B. Overall third order, 2 plus 1 make 3. First order for B and second order for A. So this is really a really important one. The rate order has to be assessed with experiments. So a couple things. If the concentration doubles, but the rate is constant, call it 0 order. Because we double, it's times 2. You see the 2 over here everywhere. 2 to the power of 0 is 1. So concentration doubles, rate is constant, 0 order. We call first order when my concentration doubles and my rate doubles. 2 to the power 1 is 2. For example, in S is K times A. If my concentration doubles and my rate goes up by factor 4, so quadruples, we call it second order, because doubling is 2 to the power of 2, so 2 squared is 4. And it could be a rate order. If my concentration triples and my rate goes up by factor 9, then it's also second order, because times 3 to the power of 2 is 9. Can also be this rate law. Finally, a catalyst. Well, we talked about it. It's not part of the reaction. It makes the reaction possible. So the concentration of my catalyst in my reaction medium is the same before and after the reaction. It lowers the activation energy of a reaction. So a reaction will happen, and it increases the rate of the reaction. And it has, when we have equilibrium, it has no impact on the value of K, but the time that we reach my equilibrium will be less. So I reach my equilibrium faster. Okay guys, that was it. Hopefully it works for you. Good luck everyone. Bye bye.